Hello, everyone. Hope you're doing well. We're going to talk about a topic today that is going to come up, especially in the latter half of this course, as we start trying to find spaces without holes, spaces that are complete, essentially. We'll talk a little bit about what completeness means in the context of a space. We'll talk about how that's related to something called Cauchy sequences and make a relationship between these two types of topics. The thing I'm talking about here when it comes to holds is this. I'm saying let's take a sequence of numbers, something like 1, 1.4, 1.41, 1.414, so on and so forth. Maybe you might notice that these are decimal approximations to the number square root of 2. But the thing is that if I'm only looking in the rational numbers, then the sequence of elements, even though the points get closer and closer to each other, they never get closer to an actual value inside of the rational numbers. And that's because we know from our very first talk that the square root of 2 is irrational. It does not fit inside of the rational numbers. In fact, the rational numbers we found are countable, while the real numbers, those rational numbers with the irrational numbers thrown in, are uncountable. So in some sense, the size of how many irrational numbers there are to countable numbers is infinite in ratio. So how am I supposed to work with a space that has all of these holes in it? And the typical thing that we want to do is try and complete spaces before we go through and do many of the results that we want to do, especially in the latter half of this course, because we're going to have some techniques in our proofs that are going to require us to have a limit to the sequences that we define, even when those points come closer and closer together and don't have a specified limit. We would like to be able to say, oh, they have a limit anyway. So we're going to take a little bit of time today and discuss this notion of complete sets. This might be something that is familiar to you in the context of the real numbers, and we'll go through that context today. As while we're doing that, we'll talk a little bit about the construction of the real numbers and how it comes as something related to the space of rational numbers. And that's exactly what we have here on this slide, asking us what a real number is. Some of the answers that I've heard in classes when I asked this question before, because I like trying to ask this question to my senior level students when we're taking a 400 level course in this sort of topic. I like to ask them, what is a real number? And one time I got an answer that was along the lines of, oh, it's a number whose square is non-negative. And I get that sort of answer. I was like, it actually is pretty good, because if you're looking at all of those complex numbers, you're saying, okay, basically it's all of the complex numbers without with a zero I component. But the issue with that is this: the way that we define the real numbers in our current system is that the real numbers come first, and then the complex numbers come after. So if I'm attempting to define the real numbers by something that's really built on top of that thing, then I'm being a little self-referential in that definition. The things that I have usually that come before this are the natural numbers, the integers, and the rational numbers. So where do the real numbers come from in all of that? So some credence comes in the answer that real numbers are limits of sequences of rational numbers. So for example, we had the sequence that we saw from before, and you could take a look at a sequence of these, of maybe approximations of pi. Noticing that these are all kind of like partial sums to these numbers that we're trying to approach, square root of 2 and pi. These partial sums are 3 plus 0.1 plus 0.04. So these are all just sums of fractions, and we can eventually come up with a way of getting to this by taking a limit of those partial sums that we're making. So the set of rational numbers we know now is filled with holes, things like square root of 2, and although we haven't proven it, things like square root of 3, square root of 5. We could get infinitely many irrational numbers this way, and thanks to Cantor, we can actually learn that the number of irrational numbers, even if we cannot make a list of all of them, and which we certainly can't, even if we cannot show where all of them are, there are infinitely many more irrational numbers than there are rational numbers. We will say that a space without the holes in this space are complete, and we'll be more rigorous with that definition once we've introduced a Cauchy sequence. First thing we need to do is talk a little bit about the completeness principle. This is going to introduce concepts that may or may not be familiar to you, notions of supremum and infimum of any non-empty sets. So here's what a supremum is for a set. Let's say that you take a set 0, 1, and let's say it includes 1, it doesn't include 0. then the supremum of the set A is the least upper bound for that set. Upper bounds are going to be any elements in which you can find that every single element inside of that set is less than or equal to that upper bound. So for example, 2 is an upper bound of this set. So is 3/2, so is 5/4, so is 9/8. You can get all of these to be upper bounds, but you know that there's going to be multiple upper bounds whenever your set is bounded above. And we'll use the term bounded above whenever we want to say that this has an upper bound to it. So the question is, what is the least upper bound? Does this least upper bound exist? Well, for the set 0, 1, it certainly does. That least upper bound is the element 1. And that's because of a little intricacy in the definition of upper bound. We say that M is an upper bound for the set A if X is less than or equal to M for all X in A. So notice here that we are allowing this to potentially be an element of A. Of course, if it's going to be an element of A, it has to be the greatest element of A, in which case they would have to be 1 in this instance. And 1 is going to be the least upper bound. 1 satisfies this property, namely that any element inside of this set A is going to be less than or equal to 1. And there's no way to go smaller than that because 1 itself is inside of the set, telling us that the supremum of the set is 1. But it's not necessarily true that a supremum or a infimum, which we will define kind of conversely as the greatest lower bound of a set, have to be inside of the set A at all. For example, the greatest lower bound of the set A, this being 0 to 1 without including 0, but including 1, the infimum of this set is still 0. That's because 0 satisfies the converse property with this if you have a lower bound. Oops. If you have a lower bound, maybe we call that lowercase m, is that we would be looking for x being greater than or equal to m, and then having everything else be the same. So if something is a lower bound, then what is that going to mean? That means that everything is greater than or equal to this value. Okay, in that side of the set. So 0 satisfies this property. So does -1, so does -2, but 0 is greater than all of these. Now, is there a greater lower bound than this? There's not. Any number that I pick greater than 0, for example, if I pick an x value that's greater than 0, well, then x over 2 is also in there, right? X over 2 is also going to be a number greater than 0. So x over 2 is inside of our set A. Well, we said that we were giving x as a as a possible lower bound. So the fact that x over 2 is an element inside of A that is actually less than this lower bound tells us that, oh, well, this candidate didn't really quite work. So no value x greater than 0 is possible to be a lower bound for this, which means that the only thing that we're left with, the greatest possible value, is the value of 0. That's a quick kind of heuristic way of how we could be going through and defining supremum and infimum. Now, for the set A equals the natural numbers, the infimum of the set is 1. Discrete sets are typically easy to find the maxima and minima for, or in this case, infimum and supremum. But the supremum of the set is infinity, and we would say that is another way of saying that A has no upper bound. If we take the set of natural numbers, then they continue to grow off toward infinity. So we would say that the supremum of A is exactly that. So it has no upper bound in there at all. So notice that the understanding of supremum and infimum is slightly different than the notion of maximum and minimum. For example, in this first set, the supremum of A matches up exactly with the maximum of A, which is 1. However, this set has no minimum. And that's because there is no minimum value, which we would define to be a lower bound that is inside of the set. Maximum of A, in this case, is equal to the supremum of A, because the supremum of A is inside the set. However, the greatest lower bound of the set, which is 0, is not inside the set. So we could not say that 0 is a minimum of A, because what the requirement for both of these is that these must be inside A. So a maximum and a minimum can exist for a set or may not exist. So think of this as like kind of generalizing the notion of a maximum or a minimum in a set. Having a greatest lower bound or a least upper bound tells us that you can extend the notion of maximum minimum a little bit to say that there is something maybe just right on the edge of that set, that the next little step that they take is actually inside of the set. So for things like the open interval from 0 to 1, with that open side on 0, you can see that 0 is right there at the cusp of that. So pictorially, if you're picturing this, you've got this picture of 0 and 1 in your head, then what you're doing is you're saying, okay, the element of 0 is not inside that set, but it's just right there. It's just right on the inside there. So 0 would be a greatest lower bound without being a minimum of a set. The Royal Numbers has something called the Completeness Principle, and this is an axiom of the set, which is that every non-empty subset A of the real numbers that has an upper bound has one that is a least upper bound. Now, this seems like something that is quite obvious looking at this example, so I like to try and give something real quick that shows you that this is actually a unique property, that not every set has this property at all. And in fact, the proposition, the set of the rational numbers is not complete, kind of helps us see this notion of that there are holes in the rational numbers. Now, let's go ahead and give that a rigorous definition of completeness. The thing in parentheses here is here to help us. We would say that a set X is complete if every set A, which is bounded above, has a least upper bound. So essentially, everything that has an upper bound has a supremum. Now, there's a converse notion to this as well. If you think about sets like taking the negative values of sets. So for example, I could define maybe the negative of a set A to be the set of all negative A values for any A inside of A. Well, then there's a corresponding notion here to using this negative A as a link to saying if every set A, which is bounded above, has a least upper bound, then every set negative A is going to be bounded, is going to be bounded below. So we are going to ask for it to have a greatest lower bound as well. So we could have made a equivalent definition here to say that every set, instead of every set that is bounded above to have a supremum, we could have said that every set that is bounded below has an infimum. That would have been an equivalent definition for our set. And that's the link between those two in order to establish that equivalence in the proof is to take every set A and this original definition of completion and take a look at the set negative A. If A is bounded above, negative A is bounded below. A supremum for the set A would be an infimum for the set negative A. And I'll leave those some sorts of details to you. Let's show this proposition about the rational numbers not being complete. Let's consider the set E, which is the set of all rational numbers where x squared is less than 2. Notice already that there's a little bit of an understanding as to why this one does not have a supremum. We are limited to the rational numbers here, and we note that if there were to be a least upper bound for this set, what we would probably posit it to be is the square root of 2. That's because these are all of the values where x squared is less than 2. So this is a set that is certainly bounded above, as no number greater than 2 could be inside of this set, for example, by the increasing nature of x squared when x is positive. So if you have any rational number that is an upper bound, something like 2, what we're going to go through and do is claim that that value, like 2, could not be an upper bound. So pictorially, what we're going to do is this. We've got a set here of all of these values inside of the rational numbers, which is right over here is where we would put square root of 2 if we had it, which we don't. So what we're going to do is we're going to establish a pattern, which is, let's say that this is a upper bound, any upper bound for this set. And what we're going to do is we're going to say, okay, given any upper bound for this set, since we cannot choose square root of 2, we're going to show that there is some other upper bound that would be lesser than it. So our original upper bound cannot be a candidate for the least upper bound. But then we're going to run into a little bit of a loop because we're going to say, okay, this upper bound is arbitrary. So any upper bound, even this lesser upper bound that I have here on the picture, could also be undercut by some other sort of upper bound. So what I end up getting is not really an upper bound, it's some sort of infinite sequence of upper bounds. If I continue this process all the way through, I get tons of choices for upper bounds, but I'm also at the same time showing none of them can be the least upper bound. So any upper bound that I might choose has one that is lesser than it, and the only conclusion that I can come up from that is that no upper bound is the least upper bound. So let's see if we can do that. Let's start with q, a rational number, being an upper bound, and let's define a value of p to be this value of q minus a positive number. How do I know that this thing that I'm subtracting over here, q squared minus 2 over q plus 2, is rational? Where I know that q is an upper bound for the set E. Well, if it's an upper bound for the set, then that means that q squared minus 2 must be greater than or equal to 0. Well, it's not going to be equal to 0 because we know the square root of 2 is irrational. So q squared minus 2 is strictly greater than 0. So q is going to be, if q is an upper bound, we have the notion that q squared minus 2 is greater than 0. Hence, by our definition, p is less than q. We also note that p is the subtraction of rational numbers. Q squared minus 2 is rational because anytime you square a rational number, you get a rational. If you divide a rational by a rational, you get a rational number. So this value of p is also in the rational numbers. Notice that that's important. We can't just say put square root of 2 in there because the square root of 2 does not exist for our set, and we're attempting to show this set is not complete. So since q is an upper bound, we've gone through that part. Note that we can rewrite p by getting everything in terms of a common denominator, in this case, q plus 2, and write p is equal to 2q plus 2 over q plus 2. Once we do that, calculating the notion of p squared minus 2 is now going to be straightforward. Why do we want to construct what p squared minus 2 is? Well, we want to say that this value of p that we define, not only is it a value that is less than this upper bound, but we also want to say that this lower value is itself an upper bound. So we're about to try and show that p squared minus 2 is indeed positive. So we go through and compute, given this value, what p squared minus 2 is. After we go through and get another common denominator, this is the value that we end up getting, which is 2 times q squared minus 2 over q plus 2 quantity squared. Again, q squared minus 2 is greater than 0, so that means that p squared minus 2 is greater than 0. So p has to be an upper bound for the set E. Since p is less than q, q is not a least upper bound, and since q is an arbitrary upper bound, no least upper bound can exist. So this is showing us that the rational numbers are not complete. Now here's a little bit of an interesting thing that is sometimes skipped over. Notice that this says the rational numbers are not complete, but you can make a similar proposition in the following way. The proposition here is that, well, z is complete. That is that the integers do not have any holes in it. So notice that this is a little bit different than comparing to how we might think of the rational numbers as being filled with holes. Well, the integers are almost all holes in terms of our picture of them. Right? The integers are a complete set. Take any collection of integers that is bounded above. Well, then there is a greatest integer inside of that set. That greatest integer is a least upper bound for that set. You can fill in the details of the proof there if you would like. But the integers are a complete set. So are the natural numbers. And in fact, so is any other sort of discrete set where there is a least distance there is a least distance between any 2 points in a set where that distance there is positive. So the notion there of discrete tells us that even these sorts of sets are complete by definition because you can always find a greatest value inside of those sets. And because of that, you can say that is going to be your least upper bound. So notice that this notion of completion is really saying that whenever you're getting points closer and closer to each other, you want it to be that those points getting closer to each other have some place in which they're going toward. The reason that discrete spaces don't have that issue is that when you have all of these points that have this notion of a least distance between them, then whenever you're taking a sequence of those points and getting them closer and closer to each other, well, at some point, there's a least distance that no two points can get closer and closer toward. So you're just ending up with a constant sequence eventually, whenever you're looking at that. This notion of points getting closer and closer to each other is related to this notion of Cauchy sequences. And before we get into Cauchy sequences, I want to give us a theorem that we're going to be seeing very much a lot here in this class. Notice here that we took a sequence of upper bounds in this previous theorem and had them kind of going toward, in some sense, a direction of where they're going toward. So we could use these sorts of principles to define these sorts of limits. Because these sequence that we were defining of, maybe we could say in this case that this upper bound is the value of P1, this is the value of P2, and then you could keep going, finding a value of P3, so on and so forth. We could notice that this sequence P1, P2, P3 of all of the upper bounds that we would be defining out of this set, again, just to be clear, what we're doing is we're saying take the first upper bound that we got, define Q to be P sub 2, the Q beginning the one that we found in this case, and then say, okay, well, what happens if I make P sub 2 my upper bound and say, can I make P sub 2 an upper bound for this set? Well, then there's going to be a lesser upper bound than that we could go through and define. But the notion is, and I want to define here, is that what if instead of just replacing Q with P in terms of some sort of finite process, what if we ended up taking a limit of a sequence of values like this? Let's say that the sequence elements got close enough to the set as we were continuing to make these happen. So let's go through and review some notions here, because we're going to need these notions as we move along, which is the notion of a monotone sequence. Notice that this sequence that we defined, this P1, P2, P3, so on and so forth, that this is a decreasing sequence. Anytime that I am positing an upper bound for this set, I am always able to find one that is less. So as I continue to up the index of this sequence here, the values of these upper bounds are getting smaller and smaller. That's the notion of a decreasing sequence. Any monotone sequence is going to be something that is either increasing, that is, that you have a sub n plus 1 is greater than or equal to a sub n for all n, or it's always decreasing. A sub n plus 1 is less than or equal to a sub n for all n. Notice that it always has to be one of these or the other. So, for example, the sequence here has increasing parts and decreasing parts, but you cannot say that it's monotone. This part is increasing, this part is decreasing. Technically, I suppose you could say the sequence is increasing here and decreasing here, and you could do that for the entire sequence. But we say something is monotone if it is always increasing or always decreasing. So increasing sequences and decreasing sequences like so. Then there's a proposition known as the monotone convergence theorem, which says that every monotone bounded sequence, A sub n and R, is actually a convergent sequence. If you are going always all the way up or going always all the way down, then you have a notion of convergence inside of this set. Here's a bit of a proof for that. Let's, without loss of generality, because the notion of this sequence where it's decreasing is similar, let's take A sub n to be increasing and bounded. Then let's let L be the supremum of this set. Notice that we can do this in R because we have the completeness axiom for this set, which tells us that every set that is bounded above, such as the set that is the sequence, has a least upper bound. So we can posit that L is the supremum of A sub n. Notice that we're already using the fact that R is complete in order to show that this sequence converges. We could not have done this in the rational numbers. Then by definition, A sub n is less than or equal to L for all n. That's because A sub n is constantly increasing as a sequence, and since this is supremum of L is the supremum of A sub n, that's by that definition there. What's more, for all epsilon greater than 0, A minus epsilon is not an upper bound, because this L that we, or rather, I guess I should have said, instead of A, I should have said L here. My apologies. There we go. So let me do that here and here. That makes a lot more sense because L minus epsilon is not an upper bound. We said that L is the least upper bound for this set. So L minus epsilon cannot be an upper bound because, well, it's going to be less than L. I guess I was writing this as A at some point as the limit here. So I need to be replacing any of these values of A with the value L. Apologies on that, so that becomes a little bit more consistent. Well, that means that there's going to exist some value n in the natural numbers so that L minus epsilon is greater than a sub n. Here's how we get to that point. We know that L minus epsilon is not an upper bound. That means that there is some element of the sequence. Maybe we call that a sub capital N, so that a sub capital N is greater than or equal to L minus epsilon. That's what contradicts the fact that L minus epsilon is not an upper bound for the set. There are elements of the set that are greater than it. Well, if a sub capital N is greater than it, then so is a sub capital N plus 1, and so is a sub capital N plus 2. That's due to the fact that the sequence is increasing. So since the sequence is increasing all the way through, then I know that actually I get that L minus epsilon is greater than a sub n. Well, if we go through and move around some of these terms, like for example, the terms that are given in this inequality here, then we find that 0 is less than L minus a sub n is less than epsilon. Or another way to say that, in fact, a little bit of a weaker way to say that, the absolute value of L minus a sub n is less than epsilon. Well, I can always switch around terms in an absolute value. That is the absolute value of a sub n minus L is less than epsilon, and that's exactly where we end up with the definition of convergence. So we find that a sub n converges to L as a result. If I was trying to do this for a decreasing sequence, sometimes this is nice to see, I could have said, okay, for a decreasing sequence, b sub n, then something I could have done is let a sub n equal to negative b sub n. Notice that if the sequence b sub n is decreasing, then a sub n equals negative b sub n will now be an increasing sequence, which I can now do the same sort of thing, find a supremum for it. Let L be the supremum of a sub n. Then by going back and negating what I have, then negative L is an infimum for b sub n. So this is kind of using that little without loss of generality, but explaining actually what's going on there, which is that decreasing sequences and increasing sequences are related by this minus sign, kind of like supremum and infimum for our sets there. So that is the monotone convergence theorem. It tells us that these increasing and decreasing sequences in R actually do converge to something, whereas here in just the rational numbers, we may not get this notion of convergence. So looking at these bounds as they continue to decrease all the way through, in the rational numbers, we could be getting all of these numbers, but they never go somewhere. Like here, they would go towards square root of 2 with this picture. But here, we see that it takes the real numbers. And the reason we know it takes the real numbers is we need to assume that these sequences have suprema and infima. And we know that rational numbers don't necessarily have that. Now, we said that we would use the monotone convergence theorem as part of a previous theorem that we went through and took a look at. Let's see if we can get that pulled up just to kind of be fluent in this. A bit of a tangent here, but if you would allow me, we mentioned back a few PowerPoint slides ago that we would be using the monotone convergence theorem to prove something called the alternating series test. Here is that theorem and the proof that we were writing. Notice that the way we were doing this for sort of theorem was we were taking S sub 1, S sub 3, S sub 5, S sub 7, and taking basically the odd elements of the partial sums in this sequence of alternating series. That means it goes positive, negative, positive, negative. And because our original A sub n is a decreasing sequence that converges to 0, we get that this is a decreasing sequence. In fact, we know that this sequence is going to be bounded below in the following way. So if you have S sub 1, S sub going to S sub 3, right? So all of these things show us that this sequence is decreasing. So we get something like this. But we would need to be able to use the monotone convergence theorem. We would need to be able to say that this sequence is bounded below. So the question is, how could we go through and do that? Well, let's go ahead and use the fact that evens are going to have the opposite property. That's what we kind of skipped over a little bit with this other part. S sub 2n, this is being the partial sums, can be written in the following way. You can take S sub 2 to be a1 minus a2, plus, in parentheses, a3 minus a4. Notice that this is a value that is greater than or equal to 0 by our definition. And in fact, all of these things in parentheses are greater than or equal to 0. So S2 is greater than or equal to S4 is greater than or equal to S6 is greater than or equal to S8, so on and so forth. And finally, notice that the difference between any of these two values that I have in the same column with each other, notice that this difference is growing smaller, namely that the value of S sub 7 minus S sub 8, that this is equal to, well, this is equal just to the absolute value of A sub 8. Notice this is because this is the sum of I going from 1 to 7 of the values of A sub I, and this is the value as I goes from 1 to 8 of the values of, or infinity instead, A sub 8 of the values of A sub I. The difference between these two is that, well, the first 7 terms cancel on each of these sums, and you're left with just A sub 8 in its absolute value. Okay, well, that means that I need to be observing what happens to A sub 8. These values are going closer and closer to 0. So in fact, these values are always have the value that this is less than or equal to this in terms of looking at the difference between here. If we're saying, for example, that all of these values in sequence are greater than or equal to 0, and we can do this without loss of generality, yeah, in fact, we have to say this because these sequences converge to 0, then we actually get this inequality outright, because the difference here is going to be that S sub 8, the thing that we're adding, is negative A sub 8, which is going to be a negative value. So we are getting that these greater than or equal to's here are always true, which means that if we take this increasing sequence, well, each element inside of this increasing sequence is going to have an upper bound. And you can show that any of these elements here in this partial sum are going to be an upper bound for this increasing sequence. Kind of in a picture sense, what's going on is you're taking a look at these being your odd partial sums here, and these being your lower partial sums. You can kind of see the notion of this alternating that's going on in between the two of them. So if we are doing this as our addition and noticing that the numbers are getting closer and closer to each other, we get that each of these have limits. So this has a limit to some value of, maybe we could call this S prime, and this has a limit to some sort of S double prime, both of these limits existing by the monotone convergence theorem. And the question is, what is the relationship between S prime and S double prime? Well, remember that the difference between any two numbers of the exact same in the exact same places in their sequences, that number is growing smaller and smaller, because that number is exactly A sub 2n, and that sequence A sub 2n is going towards 0. So in fact, due to that growing closeness as we keep going along, we see that the value of S prime minus S prime must be less than the absolute value of A sub 2n for all values of n. Well, since A sub 2n is going towards 0, that means that actually this is going to be equal to 0 in its absolute value. Since notice here, there's no n values in the indices of S prime or S double prime. These are the fixed limits of these odd partial or even partial sums. What that means is S prime and S double prime have to be the same. So this is the limit of this odd partial sums and these even partial sums. So any given sequence that we could take inside of here, if we just take the whole sequence and put it all together, all of this is going to converge to exactly that same limit. So the odd partial sums slope downward, kind of like what we see in this picture, and the even partial sums slope upward. Combining that with the fact that A sub n goes to 0, we end up finding that these all converge to the same spot. Now, there are a few details in here that maybe you're picking up on. You may be asking, like, what if we take sequences that mix up the even and odd partial sums? I'm going to leave some of those to you. Get some practice with how you might see something like this. You might use a theorem that looks along the lines of this. We're going to about to talk about something called subsequences. So we could say S sub n converges to L if and only if every proper subsequence of S sub n converges to L. So we could be taking a look at proper subsequences here to try and get some notion of what's going on. So use the fact that you could use proper subsequences here if you would like. That's not maybe not a necessary thing that you could do here, but you might be interested in trying out arbitrary subsequences of this sequence to try and see if this ends up going in the direction you'd like. Okay. So forgive the tangent there. We're back now to talking about the monotone convergence theorem. Remember what we were doing here, our kind of the realm in which we were in was we were saying, oh, let's take a look at this theorem over here and let's see what happens if you try and take upper bounds and continue to make a decreasing sequence out of them. Then the issue is we would like to take a limit of some of these upper bounds as long as they get closer and closer to our upper bound, our least upper bound of the set. But sometimes that least upper bound may not exist. We have to assume that we are in the real numbers in order for that least upper bound to exist. And that's because the real numbers is the one that has this supremum property. That is that every set that is bounded above has a supremum. Every set that is bounded below has an infimum. Speaking of these sorts of supremas and infimos, two types of limits that are going to be important to us in this class for sequences are going to be the limit superior and inferior. To explain this, I'm going to take this picture that I've shown here that takes a sequence of these little black dots that you might see throughout here, which make up the values of x sub n. Now, the black dots are also including these little black dots that you see up and down on these pictures. Those are also elements of this sequence. So you can notice that there's some sequences, elements that are inside of this little realm, as well as some things up at the very top. So let's think about what's going on with this sequence. Starting right over here, I have this, and this. So this point right here is inside of this little circled region. And the reason is that this is the greatest of all of the elements that are going to come after it. This is the greatest of all of the elements that are going to come after it. Every element past this point is going to be less than or equal to this point. In some sense, it is a supremum of a following set. This value, like given right here, is equal to the supremum of x sub n for all n greater than or equal to k. Well, if I go through this and actually define a set out of this, maybe I call this a sub k, then I end up getting a decreasing sequence. Here's how I could go through and see that. If I want to take the supremum of the set, I'm going to assume, first of all, that this supremum is bounded above, just for the sake of making this a little simpler. Otherwise, I would just be saying this supremum is infinity. So if this set is bounded above, then the supremum exists. So let's take a look at it. If I am looking at a sub 1, then I'm looking at the supremum of all of these elements, x sub n, which is n greater or equal to 1. A sub 2, on the other hand, is going to be the supremum of all the sets x sub n, where n is greater than or equal to 2. What's happening in between these two sets is that I am reducing the number of elements that is inside of the set that I'm taking the supremum over. Well, if I'm taking a least upper bound, which is, you can think of it like a maximum if you'd like, and if I'm decreasing the number of elements inside of the set, that should be making it harder to attain the same supremum that I had before. That is, a sub 1 should be greater than or equal to a sub 2 as a result of the fact that I'm shrinking the set that I'm taking the supremum over. Similarly, a sub 2 is going to be less than or equal to a sub 3, so that's going to be equal to a sub 4. And you can kind of see what this sequence looks like from what we have over here. Oops. Looks like I erased too much. So give me a moment here. See if I can get that back. 1 second. There we go. I was wondering why I had, how I had erased dots on my screen. Okay, they are back now. So you can see this notion of a sub 1, a sub 2, a sub 3, a sub 4, and see that that sequence continues to decrease all the way down through there. Well, if I take the limit of this sequence of these a sub k's for this other sequence that I have of x sub n's, then that limit is what is called the limit superior. That's exactly what is given right down here. Notice here I flipped where k and n are appearing in this sequence, but this new sequence is basically the least upper bound of the elements of the sequence that come after the value of that index of n in this case. So that is the supremum of these particular sets. I could have done the same thing for the greatest lower bound of all of the elements that come after it, and that would have given me another sequence. If I take the fact that these are decreasing and increasing sequences respectively, then I can take the limit of each of these things, since these are each bounded above or below respectively by any element in the sequence that you might give it, at least one that comes after it. So any elements here inside of the sequence will give me a bounded above or below, as long as there exists a place in which these limit suprema or infima, these sequences are infinity or not infinity. So that is when these limits can exist. So limit superior and inferior are neat ways to say, okay, maybe this sequence doesn't exist, but at least eventually I can put a bracket on where those elements of those sequences are. Taking a look at this picture one more time, I noticed that I could have started over here to say, okay, over here, this is the bracket for how all of the elements of this sequence are. But typically I'm okay doing finite cutoffs points in my sequence. So really I could say, okay, this is the bracket that I need for all of the future elements inside of this sequence. This is where most of my sequence lives, is inside of this little bracket. If I continue this sequence all the way down, then I may not get something that exists in terms of a limit for that sequence because maybe there's just too much oscillation going on. But instead, I could say eventually everything is going to be within an epsilon of this bracket between the limit infimum and limit supremum of those sets. So that's the kind of the interesting thing about these sequences. So for example, you might say, okay, well, let's take a look at the following sequences. Maybe I'm looking at something like 1 plus 1 over n to the negative 1 over n plus 1. Well, taking a look at what the sequence is doing is you're taking a look at the values of the sequence. Starting at n equals 1, you should get something like negative 2, no, just 2 for it. And then you should get something like negative 3 halves. And then you get something like, let's see, 4 thirds when I plug in n equals 3. And then something like negative 5 fourths when I plug in this. And I'm going to continue getting a little bit closer and closer to the values of 0, but I'm not going to get quite closer to 0. You might notice that the limit of this sequence does not exist as I have written it, but these values are getting closer and closer to limit superiors and limit inferiors. These two values are the places in which these values of the function are getting closer and closer to as they go along. But something interesting you might notice here is that no element of the sequence actually lives inside of this window. No element of the sequence lives inside of this window at all. And that's something that can happen for limited superior and inferior. So don't let this picture kind of be tricking you on that. You don't have to have anything inside of this window of the limit inferior or superior. And the reason is that the way that these things are approaching is that the supremums of these sets, as you make on the cutoff points, are all approaching from above, and these are all approaching from beneath. You still get the fact that these are decreasing and increasing sequences when you take a look at the sequences of capital M sub n and lowercase m sub n that we had before, but they are going toward these limit supremum superiors and inferiors from maybe the opposite sides of what we would expect. So we're saying that eventually you're within an epsilon of these limit superiors and inferiors. You cannot say that the sequence is always going to be inside of that particular window there, but you can say it is within an epsilon eventually of that little window. So for example, if I said instead of this limit infimum, which in this case is -1, this limit superior, which is in this case 1, then I can't say that the sequence eventually lives within the sequence or within the set -1 to 1, but I could say it lives eventually within the set -1 minus a million, and I could say it lives eventually within the set -1 plus 1 million, 1 over a million. So I can absolutely say this, because now that I've even just created a little bit of epsilon, eventually all of the n values past that, which are going to be the n values past a million in this case, those n values are going to be inside of that little window plus that epsilon. So eventually the sequence is going to always be inside that window. So it's a little bit like a generalization of limit, because limit, we say if these are always within an epsilon close window of a single point, whereas here we're saying that this is within an epsilon close window of this window between the limit inferior and superior. Notice that we can use this as a characterization of when a limit exists, and this is going to be useful for us in the future as well. So we'll go ahead and record this proposition. That is, if a sub n is a sequence, then you get a limit for that sequence, a sub n, which is b, if and only if the limit supremum superior, I keep saying that. It's because it says sup there, so if you say that too, that's going to be fine. But the limit superior of a sub n is equal to the limit inferior of a sub n is equal to b. Essentially, you're saying that the limit exists if and only if you take limit superior and inferior and make them equal. This makes sense with our kind of window notation, because we were saying, okay, in order for a limit to exist, you need an epsilon window around that point to always contain any point past your sequence, right? Past a cutoff point in your sequence. Whereas if your window of limit superior and inferior grows to or shrinks to have length 0 between the superior and inferior, that is, that these two things are equal, well, then you're doing the same thing. Epsilon close to that window is epsilon close to that specific point at which they both equal. I will be asking you to prove the squeeze theorem as a part of an exercise here, which means you cannot use this proposition in order to do that, just to be clear. But I will ask you to go through and prove the squeeze theorem, which is going to take this fact, the fact that m sub n is less or equal to a sub n is less or equal to capital M sub n, given that these are the sequences that we had from before, and show that because all of these sequences of little m sub n and big M sub n are going toward the same point, the sequence a sub n must also go to the same point. That will be an exercise to be working on. Again, you cannot use this proposition to do that because we are using it in the proof of this proposition. Instead, use this notion of kind of the inequalities that we've been working with and show using the definition of a limit that you get something like that. That shows us this right statement implies the left statement. For the left statement implying the left statement, if you have the limit of a sub n is equal to b, well, then remember what that means is that you're always going to get a cutoff point for the value a sub n minus b. Notice that this means that negative epsilon is going to be less than a sub n minus b. It's going to be less than epsilon for n greater than or equal to big N. Well, if I rewrite that latter half of this statement, then, for example, adding b to all sides, then I actually see that a sub n is going to be in between b minus epsilon and b plus epsilon past any cutoff point. What that means is this: the limit superior of this function has to be less than or equal to b plus epsilon, because past this cutoff point, remember, you have a decreasing sequence. You're going to have that m sub n, in this case, is also less than or equal to b plus epsilon, because every element past that cutoff point is going to be less than or equal to b plus epsilon. Similarly, lowercase m sub n, that's going to be less than or equal to b minus epsilon. Oops, looks like I need to go the opposite direction. It needs to be greater than or equal to b minus epsilon. And so because of this, the values of m sub big N and big M sub big N, those values are going to get scrunched closer and closer together as we shrink the notion of epsilon. We are just letting epsilon go to 0. This is a trick that you often see in these types of proofs. If you get something that works for all epsilon and you notice that you get the value that you would like whenever you let epsilon go to 0 in both of these cases, because as we put these together, for example, we get b minus epsilon is less than or equal to m sub n is less than or equal to big M sub n is less than or equal to b plus epsilon when we combine everything together. If we let epsilon go to 0, what we're essentially doing is taking a limit of these big N's. If we do that, then, well, that limit is going to be equal to, as n goes to infinity of m sub n, it's going to be equal to b, as is the limit as n goes to infinity of big M sub n. That also must be equal to b by these lower and upper bounds that we're working with. Okay, so that gives us a little bit of another perspective on how we can solve for limits of sequences. This one is surprisingly useful. You'll hear me use these notions of how we define the sequences m sub n and big M sub n every now and then. I will kind of throw these back on us as we kind of go around. So, because this way of superior and inferior to show these sorts of limits is surprisingly very useful. And we'll see it a good bit as we kind of move along. Let's go ahead and see one way in which we can use these, and we might see it in work at some point. Let's show that the limit superior of the sequence a sub n plus b sub n is less than or equal to the limit superior of a sub n plus the limit superior of b sub n. And then let's try and find some sequences a sub n plus b sub n so that the equality does not hold. Well, what we're going to have to do here is think a little bit about these definitions. So let's be clear about what these definitions are. Remember that the limit superior then goes to infinity of a sub n plus b sub n is going to be equal to what? It's going to be the limit as n goes to infinity of the supremum of the following sets. Supremum here, this is going to be for n greater than or equal to k, of the set of all a sub k, or a sub n plus, make sure I get it right. This is going to be for, just make sure that I get this right. Oh, yeah, there you go. Sorry, I had to get some of my indices written the right way. The limit as n goes to infinity for the supremum of this for all k greater than or equal to n of the value a sub k plus b sub k. I could have written this perhaps in a way that was more standard to how we wrote this in the class, which is here we're saying that k is greater than or equal to n, instead of writing it underneath the supremum. But if I had written it like this, and instead of writing it here, that would have been the same thing. So here we go, get something like this. So we're taking the limit of this sequence, and we're trying to compare this to what happens when you look at the limit as n goes to infinity of the supremum of a sub k for all k greater than or equal to n, and adding that to the limit as n goes to infinity of the supremum of b sub k for k greater or equal to n. So we're trying to make some sort of comparison between these two values, because this right here is the limit supremum of a sub n. This is the limit superior of b sub n. Go. So how am I going to compare these two values? The difference here is this. When I write out the definitions of each of these things, I see that there is one supremum being taken of this set, and it's of the two sets being added together, whereas here, the addition, instead of happening inside a set, in the place that I'm trying to end up in, the supremum ends up happening outside the set. What we might do here is start thinking about some examples of things that might make this stuff make sense. Here's an example that immediately comes to mind when I think about this. Let's take a sequence a sub k, and let's say, for example, this is just an example, that this is the alternating sequence -1, 1, -1, 1, but let's have this one start at 1. So when n is equal to 1, this is -1 squared, and this is equal to 1. On the other hand, let's let b sub k start at -1 instead. Let's let this be -1 to the n. Then notice that a sub k plus b sub k is actually going to be 0 regardless of my number of k. You can check this out for yourself. Notice that whenever this value is -1, that this value over here is going to be 1, and vice versa. Whenever this value is 1, this value is -1. So the sum of these two is always going to be equal to 0. The supremum here is going to be 0 each and every time, whereas the supremum of each individual sequence past that is going to be 1. I think already what I've done is I have found a sequence in which equality does not hold, but it was just in trying to discover, okay, what's actually going on here in this sequence. I started playing around with what kinds of sequences might make this not work, right? Where might it be that a sub k plus b sub k work in such a way that the supremum of a sub k plus b sub k does not match up with the supremum of a sub k and supremum of b sub k. That also gives me a little bit of a reason as to why this might be a less than or equal to inside of here. And that's because the supremum of a sub k plus b sub k, well, a sub k and b sub k might be working against each other at some point. Kind of like how a sub k and b sub k work against each other in terms of one being always positive, the other one being negative, and kind of canceling out the other term as you go around. Well, I've already found my latter part to this example. So this is to show equality does not necessarily hold. And that's from these two examples. Because a sub k plus b sub k is equal to 0, which implies that the limit superior of a sub n plus b sub n is equal to 0, because this supremum is always just the 0 function. So this is, or the 0 sequence. So this is constantly 0 throughout. Whereas the limit superior of a sub n is equal to the limit superior of b sub n, which is equal to 1 for each of those things. My recommendation is to fill in some of the details there to show that this is actually the limit superior of each of these sequences, but we get an idea as to why. Any cutoff point that you put in the sequence, you're always going to be able to find a 1 there. And the only values being -1 and 1, that means that the supremum of these sets of sequence elements past the cutoff point is going to be just 1. Similar for the inferior, if we needed to go through and do that, that would be -1. But to show less than or equal to here, I need to do something that helps me make sense of the supremum of a sub k plus b sub k. Well, let's think about this. The choice that I have here is that these k's have to be exactly the same. Notice that I could make this supremum a little bit more, have a couple more elements in it if I did the following. Let's see how I could compare this to the following. Limit as n goes to infinity of the limit supremum, or just the supremum in this case, of a sub k plus b sub l. where k and L are greater than or equal to n. Notice the difference between these two sets that I have defined. The first one says a sub k and b sub k have to have the exact same index. And that's because when I'm considering the sequence a sub n plus b sub n, that sequence has the same index for each of those two elements. Whereas notice here I am expanding the number of elements inside of this set, meaning that the supremum of that set can only be bigger. And hence the limit of that can only be bigger by our comparison test. So this says the limit as n goes to infinity of the supremum of a sub k plus b sub L. Well, at this point, a sub k and b sub L are not really interacting at all. I could really just take a look at these two things as individual sets. The supremum of a sub k for k greater than or equal to n, plus the supremum of b sub L for L greater than or equal to n. The only thing that could possibly happen by breaking apart these two sets is that I get something greater. So notice here that I am actually going to get another less than or equal to sign here. This is because of the reason that we were talking about with those two sequences before. It's possible that a sub k and b sub L in some ways are they are interacting with each other in a way that cancels each other out. Maybe a sub k is always positive, whereas b sub L is going to be negative except in very specific instances, in which case you could get another less than or equal to by breaking this apart as the supremum of a sub k plus the supremum of b sub L. You're now taking the supremum of this set and saying, I want that to be as big as possible. And then the supremum of this set and saying, I want this to be the biggest as possible. And that can get us to this point. Well, that gets us exactly where we would like to be. This is where we began, which was equal to this, which is less than or equal to this, it's less than or equal to this. And finally, this is by definition equal to the limit superior of a sub n plus the limit superior of b sub n. Okay, whew. So we did it. We found a way to break apart these sequences in a way that made a little bit of sense to us. We can look at individual sequences and see that equality does not hold as a little bit of intuition guiding as to why this sort of theorem might be true. So notice the steps that we're taking here and kind of allowing these two things to break apart. One step going from here to here might be a little bit tricky because why do I need these two indices to be different? Well, think now that I'm taking the supremum of this set plus the supremum of this set, the indices here do not need to be the same at all. They don't have to be the same. So this intermediary step helps to explain to somebody else and says, oh, okay, that's why I'm able to break apart the two superiors here, because now the indices have nothing really to do with each other. The only thing that I could gain from this is maybe potentially gaining more value inside of that set. That is something that could happen. By the way, it might be interesting for you to note is this less than or equal to that we have actually an equality? This is something that I would like to encourage you to take a look at. Could we actually say that this less than or equal to is an equality here due to the fact that we have two indices here? My initial conjecture is that yes, you could say that that is an equality there. So I encourage you to try and take a look at that there. The idea is if you have values of a sub k that make this set a supremum and values of b sub k slightly different that approach this superior, then you should be able to just add those two elements together and take a look at their superior and get that to be inside of this set. That should give you that these are actually equal. The way that you, by the way, show that these two values are equal typically is you want to show the opposite direction. We've already convinced ourselves in this less than or equal to sign. So the exercise that I'm having you kind of take a look at here is this one. Is it true that supremum of a sub k plus b sub L for k and L being greater than or equal to n is actually greater than or equal to the limit as n goes to infinity of the supremum of a sub k for k greater than or equal to n plus, and because the letters here don't matter, I'm going to be a little bit more consistent with how I've written L for the subscript of b. So I'll write down here the supremum of the sets for b sub L, where L is greater than or equal to n. Is it true that that's actually greater than or equal to? So that's what you want to try and show here. If you show it's less than or equal to and greater than or equal to, then you've shown that these two values are equal. So my recommendation is to try and show this. If you aren't able to show it, try and find a counterexample instead. See if you can find different sequences that make these sets not work. That is my recommendation for you as a little exercise based off of this. Now we're finally at the point where we can talk about some Cauchy sequences. Although the sequence that we've been looking at does not converge in the rational numbers, it does have an epsilon neighborhood where the sequent elements can live that shrinks as the sequence continues on. Here, I've given another example of a sequence like 1 minus 1 over n. It's kind of a bit of a picture here where you can see that these points continue to, even if they never reach a particular value, or at least maybe who knows what value that they might reach, they do end up getting closer and closer to each other. When I was an undergrad, as peers, we would talk a little bit about how we can understand some of these words like Cauchy Criterion. We know Cauchy is the one responsible for many of the rigorizing elements of analysis. So this is the name that came from, but we made a little bit of fun at the name. We would say, okay, a Cauchy criterion, the Cauchy sequence, what this is you're getting more and more people on a couch. So this is really the Cauchy criterion. You're getting a lot more people on a couch and you're having them get closer and closer to each other as they come along. And that's exactly what we're doing with this definition of Cauchy sequence. If you take a sequence of vectors in Rm, then we say that something is a Cauchy sequence if whenever you have an epsilon greater than 0, then past a certain cutoff point, any two elements inside of that sequence, the distance between them is less than epsilon whenever you have those two elements past that cutoff point. So that is our definition of Cauchy sequence. Now, you might struggle to find Cauchy sequences that don't converge in R, but we have gone through and seen Cauchy sequences that do not converge in the rational numbers, namely this one right here. This one, if you take a look at any two elements inside of this, any two elements past 1.4.414 are going to be in between the values of 1.414 and 1.415, because as the pattern of the sequence suggests, all numbers past this sequence are going to have 1.414 as their starting point. So these values are going to be within an epsilon window of each other. They're going to be within 0.001 of each other. And then if I went down to the next cutoff point, the sequence elements past that are going to be within 0.0001 of each other. So those epsilon values are going to continue to shrink as we move along. Every convergent sequence is Cauchy is something that maybe comes immediately to us, but it's something worth a proof. Convergent sequences, in order for them to converge to a value, all the sequences must eventually get close enough to each other. And what we're going to do is a quick epsilon over 2 argument to make that work. Let's take a sequence of vectors a sub n and have them converge to the vector a. Then for any epsilon greater than 0, there is a cutoff point for the sequence so that a sub n minus a in distance is less than epsilon over 2. Now, where's that epsilon over 2 going to factor in? Well, remember that I want the sequence elements themselves to be closer to each other. I don't necessarily want them all to be close to one individual point. I want them all to be close to each other. So what I'm really trying to analyze is a value a sub n minus a sub k. Well, I can introduce a value at no cost as long as I'm doing a triangle inequality to break these things apart. And that's exactly what I'm doing over here. What I'm doing is I am breaking this apart in the following way. You have a sub n minus a plus a minus a sub k. So if I take this and break it apart like this, that's what I have in this sense. And this part of the inequality train here, well, each of these things past a certain cutoff point are going to be less than epsilon over 2. And if I just take those and add them together, I get them to be less than epsilon. The only difference that I have made going from this step to this step is that I have switched the two terms in here as to be a bit more suggestive as the fact that this looks like the sequence a sub k converging to the vector a. And I'm allowed to do that because the distance between the vector a and a sub k is equal to the distance from a sub k to a. The order there of the two things is not important. So we're saying that the norm here is the same regardless of if I were to put in a negative inside of that little distance. So that tells us that convergent sequences are Cauchy. Now, Cauchy sequences in R, we want to say converge as well. We want to say that these two things are the same. So the way we begin that is that we start by saying, okay, all Cauchy sequences in R are going to be bounded. So let's apply epsilon equals 1 to the definition of a sub n being a Cauchy sequence to get that there is some cutoff point n, so that whenever you have n greater than or equal to big N, that a sub n minus a sub big N is less than 1. Notice that a few things have changed here in this sentence from the normal parts of the definition of the Cauchy sequence. Namely, I am putting a cutoff point and a specific epsilon value. Since I know that I'm starting with a Cauchy sequence in R, I know I can plug in any value for epsilon. I only need the fact that epsilon equals 1 here. In fact, I really could have done this with epsilon equals 2. I only really need the fact that this works for a given epsilon. But I have it works for all epsilon, so I'll just pick the simplest one. Epsilon equals 1 in this case. 2, usually I have for any n and k greater than or equal to big N, that a sub n minus a sub k in distance is less than 1. But because I'm saying that this is n greater than or equal to big N, well, n here I'm just saying take the definition of Cauchy that we had from before and make k equal to big N. So big N is making the difference here. So even here, I'm making a slight relaxation of the definition of Cauchy, just getting closeness to this particular cutoff point. That's going to be enough for me, as we're about to see. Then notice that for anything past this cutoff point, you can make a upper bound for the value of a sub n. And here's how that's going to work. I know that past the cutoff point, any element of my sequence I can get to be within 1 of this, whatever the value of this cutoff point is right here. So the upper bound of this is going to be whatever that value n is plus 1, because if this always is going to be inside of this window from the cutoff point that I have, then I just have to go up by that 1 in that cutoff window to get a upper bound for this sequence. Well, that's going to work for anything to the right of this cutoff point, but what about elements that are coming before it? For elements that come before it, I just need to take a max with those elements that come before it. Since there's finitely many of them, I can take a maximum of finitely many elements. The thing that we are trying to stay away from here is attempting to say that this is a maximum of infinitely many elements, because we know that maximum of infinite sets do not have to exist. Like, for example, taking the set of all 1 minus 1 over n for n in the natural numbers, this has a supremum of 1, but does not have a maximum for it. So the maximum here ends up being an upper bound. Well, John, why don't we just replace maximum with supremum? Because then we are assuming what we're trying to prove. We're assuming that this sequence that we have is bounded to begin with. We are constructing a bound in this particular proof. We could do a similar thing for finding a lower bound by taking the minimum of all things that come before this sequence and then going to that lower bound of the everything past that particular cutoff point for this sequence. We have a finite number of things we're taking the minimum of, and that gives us a lower bound for the sequence, allowing us to finally prove that all Cauchy sequences are bounded. Now that's a lemma for what we want to do is just say that all Cauchy sequences in R converge. Notice here that we're going to need to use some notions of limit superior and inferior. The notions of these limit superior and inferior existing at all, remember, these are supremums of sets and infimums of sets. Because limit superior and inferior exist, we have to have the suprema of sets and infima of sets exist without us having to think too much about it. That is the notion of completeness. So that's where completeness is coming in here in this proposition. In order to say all Cauchy sequences in R converge, we need to have that these sequences for superior and inferior actually exist. And in doing so, we have to have completeness for our set. So by our lemma, we know that we have Cauchy sequences are bounded. If Cauchy sequences are bounded, that means that the limit superior and limit inferior for these sets are finite. We can now show that if we can show that they are equal, then we are done. And that's exactly how we're going to use the definition of Cauchy in this instance, which is that you can say that past a certain cutoff point, any element of the sequence past that cutoff point will have distance from that cutoff point element less than epsilon. Well, that means that m sub n is going to be less than or equal to the absolute value of a sub n plus epsilon for this value of, really, I suppose this should be m sub capital N, should be less than or equal to the absolute value of a sub n plus epsilon, and n sub capital N needs to be greater than or equal to the absolute value of a sub n minus epsilon. All right, so this is telling us kind of where these sequences are going. Now, this absolute value can be a little bit tricky here because what if our sequence is negative, in which case I would actually need this to be the negative value, wouldn't I? So that's something to kind of keep in mind here. The real important part, though, is not really this plus or minus here, because this could really be a plus or minus in this case, or maybe a plus or minus here in this. So there's a couple of different things to play around with in here. But the important part is that whatever these two values are, if a sub capital N is positive or negative, that they are the same parity. Meaning that when I subtract these two things together, that the limit superior sequence value, m sub n and m sub little n, is less than or equal to 2 epsilon. So over here, I might need to be putting a couple of quote lines to say that maybe these two things aren't exactly what they need to be because of the absolute value. We have to ask the question, what if the sequence is negative? But that just ends up being another case for us. Then once we get through that point, we get that m sub capital N minus little m sub capital N is less than or equal to 2 epsilon. And once again, we let epsilon go to 0. That means that the limits of these two sequences are equal, which means that the limit exists for the sequence based off of our previous proposition. Whew. Once again, pretty good, pretty good. We have found that convergent sequences are Cauchy and Cauchy sequences converge. By the way, this is another way that we can use to define completeness. In fact, let's see if I have that over here in this next slide. I do not, so let me go ahead and say that this is another definition. We say a space X is complete if all Cauchy sequences in X converge. So that gives us a definition for this space. We can say that if you have a complete space, then all Cauchy sequences in X converge. And if all Cauchy sequences in X converge, you can actually say, okay, there's going to be a supremum for every set that you make, there, as long as it's bounded above. The idea behind this opposite direction of the proof is, let's say that you have a supremum. Well, then there's going to be points that continue to grow closer and closer to that supremum. That's the idea behind least upper bound, right? For example, if L is that upper bound for a bounded above set, then L minus epsilon cannot be the least upper bound. So there has to be some sort of element underneath there. So you can construct an increasing sequence of points that gives you a chance to get that it's going to be bounded above. And you're going to be able to determine that those things converge by the notion of completeness by our previous proposition. Now you're going to be able to say, okay, any Cauchy sequence in here, you can find some sort of increasing subsequence or decreasing subsequence in kind of a similar way and show that hence the sequences converge. That's a neat little connection there between these two definitions. If you'd like to try and fill in some of those details, then that's totally fine. I'd be happy to take a look over that at some point. Although we only define limit superior and inferior for the real numbers and not these vectors r to the m, we now have that each component of a Cauchy sequence in Rm is going to be Cauchy. That's by our definition of Cauchy, is that the distance between any 2 points has to be less than some epsilon. Well, that means for any two components, if you take a look at them in terms of the real numbers, these also have to be less than epsilon. So each individual element is going to be less than epsilon. So each individual coordinate is going to converge on its own. Since there are finitely many coordinates, as we've been talking about from before, having finitely many things converge means that you can make them all converge if you get past some sort of cutoff point. Then all Cauchy sequences in Rm converge as well. Gives us a neat little connection there. Let's end up here with one last thing, constructing the real numbers. Here I'm going to use something called an equivalence relation. Let me go ahead and define an equivalence relation, or in fact show you an example of an equivalence relation. We could say that two fractions, two rational numbers, are equivalent if, say, for example, whenever I write one rational number as a over b and another rational number c over d, if AD equals BC. Notice that this is our way of writing rational numbers, as being equal. Like, for example, 1/2 equaling 2/4. Right, you can notice there that if you do what we call cross multiply, then those two numbers are going to be the same. That's using this equivalence relation. In fact, the way that we define the rational numbers is really, we start with the formal set of a over b, where here a is an integer and b is a natural number. But we usually go ahead and form a partition of that set with respect to this equivalence relation. And here's how that sort of thing looks. Every element inside of this set is really not just the fraction itself, not the fraction 1/2. It's really the equivalence class of 1/2. It's the set of all elements that are equivalent to 1/2. That is, all values x such that 1/2 is equivalent to x. So this is the set of all elements equivalent to 1/2. That is our notion of an equivalence class. And our notion of how the rational numbers work is that a over b for these values given here are all not really just the elements themselves, they're all equivalence classes. So this is the set of all equivalence classes. A over b. We typically don't write the brackets there. That's just something that we're using to specify that we're looking at everything that could be equivalent to 1/2 rather than just 1/2. But when I write 1/2, I know implicitly in my head that I'm also looking at 2 over 4. I also know that I'm looking at 3 over 6. Because under my notion of equivalence, these are all of the same thing. That's exactly what we're doing with an equivalence relation. We're saying that these are all of the same thing. Now, not all relations are equivalence relations. There are some principles that we'll talk about in a later section that make something an equivalence relation. But this thing that I have here is an example of equivalence relation. And I'm going to go through and define another equivalence relation on the collection of Cauchy sequences of rational numbers. So for example, I'm looking at sequences of 1.4, 1.41, 1.414. And I can also look at Cauchy sequences like 2, 1.5, 1.42, 1.415, and so on and so forth. Taking a look at these two sequences, you can see that what I'm attempting to approach from each of these is the value of square root of 2. But I would like to think about these two sequences as really approaching the same thing. Even if square root of 2 is not defined in my space of rational numbers, I would like to be able to say that these sequences are the same, in the sense that where they end up approaching, or the sense that they get close to each other, is the fact that these sequences themselves are going towards 0 when I consider their difference between the two of them. For example, if I take the difference between 2, 1.5, 1.42, 1.415 with 1, 1.4, 1.41, 1.414, then I know that these two sequences are approaching the same number, because when I take a look at the difference between these two things, I have a sequence that is going towards 0. So this sequence going towards 0, okay, that is something that I could maybe base an equivalence relation off of. The fact that these two sequences are getting closer and closer to each other means that these two Cauchy sequences kind of have the notion of closeness in between the two of them as well. So we would like to be able to say that these two sequences approach the same value. Now, in the rational numbers, these two things are approaching the square root of 2. So I can't actually say they approach the square root of 2. So I can't just say, okay, they approach the square root of 2. So the little way that I try and get around that hurdle is that I'm about to define the set of real numbers as if they are these sequences. Notice that I'm not breaking any rules here. The things that are inside the set of Cauchy sequences of rational numbers, they're just rational numbers. I can never make one of these elements equal to the square root of 2, for example. But if I consider this collection of Cauchy sequences in the rational numbers and define an equivalence relation where, for example, these two would be equivalent because the sequence a sub n minus b sub n goes towards 0, then the equivalence relation induces a partition of S, very similar to this. We can take the set of all equivalence classes inside of this relation. Then we define the real numbers to be the set of all Cauchy sequences in the rational number partitioned out by this equivalence relation. So for example, the equivalence class of this sequence that we've been looking at would be named square root of 2. That is, that this value here is going to be square root of 2, as is this value. We're going to be able to call both of these sequences the square root of 2, just like how we can call 2 over 4 and 3 over 6 1/2, because we're saying these are the same thing underneath this equivalence relation. So this 1, 1.4, 1.41 sequence gives us square root of 2. So does 2, 1.5, 1.42. That gives us square root of 2. As do all other types of Cauchy sequences that might approach this value. For example, 0, 0, 0, 1, 1.4, 1.41. All possible Cauchy sequences that approach square root of 2 are eventually going to approach each other. And that means that the difference between them is going to go towards 0 when I take that limit. In defining the real numbers, I never had to use the real numbers. I just had to use rational numbers. That's all that I needed. And because of that, I can now say I have constructed the real numbers from something that does not come from this. And this, to me, is only one of the ways of constructing the real numbers, but to me, this is the most intuitive based on what we've gone through so far. The fact that Cauchy sequences are themselves real numbers because I'm just kind of adding in their limits. I'm kind of filling in the holes by making these Cauchy sequences that don't necessarily converge equal to what these real numbers are, the missing gaps that I'm looking for in the rational numbers. One last problem here is I'll ask us to kind of take a look at this definition a bit in our homework. Let's take a sub n here with the brackets to be the equivalence class of the Cauchy sequence a sub n in the rational numbers. Let's show that the equivalence class a sub n plus the equivalence class b sub n equaling the equivalence class a sub n plus b sub n is a well-defined operation. Remember, we talked about well-defined in a previous talk, and that was saying that in order for something to be well-defined, you need it to be the case that no matter if you wrote things that were equal here for these two sequences, that you get something that is still inside of the same equivalence class over here. So the way we have to start this is, in order to show this is a well-defined operation, we have to say, start with some representatives, and I might call them a sub n1 and a sub n2, that these are two sequences inside of the equivalence class of a sub n, and b sub n1, b sub n2, that are inside of the equivalence class for b sub n. So what we're doing is we're starting with any two elements that are inside of this Cauchy sequence, or inside of this equivalence class, corresponding to the Cauchy sequence of a sub n is given up above here. Here, these do not have to be equal to a sub n. They could be any two elements in this equivalence class, but they have to share the fact that, well, they are equivalent to each other. Then a sub n1 is equivalent to a sub n2 because they are in the same equivalence class. Any two elements inside of an equivalence class are equivalent not only to a sub n, they're also equivalent to each other. Well, what is our equivalence? We're saying that that means that the a sub n1 minus a sub n2, that this sequence converges to 0. Similarly, we have that b sub n1 is equivalent to b sub n2. So this means that b sub n1 minus b sub n2 is a sequence that converges to 0. So what are we going to need to be able to say about this? We need to be able to say that when you add these two sequences together, that you get something that is still in the equivalence class of a sub n plus b sub n. Let's see if we can do that. So we want to show that whatever happens when we add these sequences to each other, for example, a sub n1 plus b sub n1, or a sub n2 plus b sub n2, adding them across each other to each of these different equivalence classes, I want to be able to say that this is still in the equivalence class of a sub n plus b sub n, that this is in the equivalence class of a sub n plus b sub n. Well, how am I going to do that? I'm going to use the fact that, well, each a sub n given here in this equivalence class, that this is a sub n1 plus b sub n1 minus a sub n plus b sub n. And I want to go ahead and do some steps to show that this limit of this sequence is equal to 0. Well, let's see if we can do that. So I'm going to take this sequence and I'm going to start breaking it apart into things that make a little bit of sense to compare with each other. Namely, a sub n1 is in the equivalence class of a sub n, and b sub n1 is in the equivalence class of b sub n. And I can notice here that this is actually going to go to 0 when I go through it, and that's because a sub n1 is in the equivalence class of a sub n. B sub n1 is in the equivalence class of b sub n, So this is going to go to 0 plus 0, and that's equal to 0. So that's going to imply that a sub n1 as a sequence, rather, a sub n1 plus b sub n1 is in the equivalence class of a sub n plus b sub n. We could do a similar thing to show that a sub n2 plus b sub n2 is inside of there. Similarly, a sub n2 plus b sub n2 is equivalent to a sub n plus b sub n. So a sub n1 plus b sub n1 is equivalent to a sub n2 plus b sub n2. And that is by something called the transitive property of the equivalence relation. If this is related to this, basically if these two things are equal and these two things are equal, therefore this must be equal to this. And that gets us to where we want to be. So that's how we can use equivalence relations to show that now we can add numbers in this world of Cauchy sequences and get a well-defined operation. They're not just equal as sets, they're equal in terms of how they add as well. You can add Cauchy sequences by adding the individual components of those Cauchy sequences, kind of like what this problem asks us to do. But that'll do it for us today. We had a really good discussion on the notion of completeness, about how sequences can get closer and closer to individual values and help us out there. We've seen multiple different perspectives on this, starting from superior, supremum and infimum, then going to limit superior and limit inferior, and having those two things be equal to talk about how sequences work there. And finally, ending up with this notion of Cauchy sequences, that we can characterize complete spaces as those where Cauchy sequences converge. We've also seen a few examples of how we can use limit superior and inferior, as well as how to apply equivalence classes of Cauchy sequences in order to construct the real numbers. But that'll do it for me today. Thank you so much. Have a wonderful day.